Rules of quantum physics state that an unobserved photon exists in all possible states simultaneously, but when observed or measured, exhibits only one state. Entanglement occurs when a pair of particles, such as photons, interact physically. A laser beam fired through a certain type of crystal can cause individual photons to be split into pairs of entangled photons. These photons can be separated by a large distance, hundreds of miles or even more. When observed, photon A takes on an upspin state. Entangled photon B, though now far away, takes on a downspin state. The transfer of state between photon A and photon B takes place at a speed of at least 10,000 times the speed of light, possibly even instantaneously regardless of distance. This is a basic tenet of quantum mechanics. Based on Heisenberg's uncertainty principle, one cannot simply observe a quantum particle, in this case a photon, without permanently changing that particle's quantum state. That's the wrong Heisenberg. That's the right Heisenberg. With quantum key distribution, a secret key is shared between the transmitter and receiver, and if a hacker tries to decode the signal as it travels from one to the other, the signal itself changes on a quantum level. So the system detects the hacking event, the secret key is discarded, and the signal is broken, preventing the hack from continuing. Quantum entanglement has moved out of this world and into space. In a study that shows China's growing mastery of both the quantum world and space science, a team of physicists reported that it yearly sent intertwined quantum particles from a satellite to ground station separated by 1,200 kilometers. The result is a stepping stone to ultra-secure communication networks and eventually a space-based quantum internet. Starting in the 1970s, however, physicists began testing the effect over increasing distances. In 2015, these tests measuring entangled electrons 1.3 kilometers apart showed once again that Einstein was right, and that spooky action at a distance is real. Beyond the fundamental results, such experiments also point to the possibility of hack-proof communications. Long strings of entangled photons shared between distant locations can be quantum keys that secure communications. The Chinese team had to overcome many obstacles, including keeping the beams of photons focused on the ground station as the satellite hurtled through space at nearly 8 kilometers per second. However, the team recovered only about 1 photon out of every 6 million sent from the satellite. Far better than ground-based experiments, but still too few for practical quantum communications. Other countries are inching towards quantum-based experiments of their own. Scientists from China, teaming up with physicists in Australia, send quantum information between 2 satellites, and European and U.S. teams are proposing putting quantum instruments on the ISS to test whether entanglement is affected by a changing gravitational field by comparing photon that stays in the weaker gravitational environment of orbit with a tangled partner sent to Earth. The first commercial quantum cryptography systems became available in the early 2000s. People have repeatedly attempted to bring them down with significant success. The attacks have ruthlessly exploited imperfection in the equipment. In doing so, hackers have shown that if the laws of physics offer perfect security, equipment cannot be perfect. A shortcoming they've exploited is that data is often coded in the polarization of a photon. A vertically polarized photon might encode a 1 and a horizontal polarization of 0. One hack is to shine a high-powered laser into the equipment so it reflects off the polarizers inside. The reflections reveal the orientation used to polarize and encode the outgoing photons. That reveals the code. To counter this, physicists have developed ways to prevent these reflections. One new technique is called injection locking. This is a method of changing the frequency of a laser by injecting photons with a different seed frequency into the lasing cavity. Provided the difference in frequency is small, the laser eventually resonates with the seed frequency. An obvious countermeasure is to use devices known as isolators, which allow photons to travel in one direction but not the other. And there you have it.